Okay, good morning everyone. I hope everyone can hear me again. So if you can hear me, can someone just type hello in the chat, something like that? Yeah, great. Okay, good. And hopefully you can see the picture now as well. That's good. So we've got 9 or 10 people here, which is good showing for the first Friday, I suppose. Okay, so towards the end of the last lecture we were looking at this transimpedance amplifier, which was for amplifying current sources. Let me just get a pointer up. And we were looking at this kind of circuit that we've got over here, where we were amplifying a current source through the virtual ground, and we were converting the current into a voltage through this resistance here, and that generated an output voltage at the op-amp. So the op-amp is maintaining its output voltage to keep 0 volts between these two inputs. So it's the virtual ground operation. So the clever bit that's going on in here is that it's looking at its inputs, trying to keep them 0, and moving its output to try and maintain that. And that means that we generate a voltage here which generates or allows an equal and opposite current to flow. And the nice thing about this is if we have any type of capacitance across this virtual ground, or any kind of impedance at all in fact, then it doesn't really affect the operation of this circuit, because this capacitance has the same voltage at either end, and if something has the same voltage at either end, then no current can attempt to flow through it. So it's like it's not there in the circuit. So the virtual ground is meaning anything in this part of the circuit here is effectively going to be nulled out, which is great. And that's good, because in these sources or current sources, particularly sort of photodiode ones, there's a sort of a little capacitance built into the junction, and that capacitance has to charge and discharge normally. So if you can actually short it out with the measuring system, then that allows you to extend the bandwidth, because anything involving capacitance introduces delays, and anything introducing delays introduces bandwidth limitations. And that was all great and in theory, except the problem is that the gain all relies on this having a very, very high gain, and the gain of this is unfortunately is dependent on frequency. So as we move to high frequencies, we tend to find that the gain of this, the open loop gain of this, tends to fall away, and that means that the virtual earth starts to not be as effective as it once was. And then if the virtual earth is not effective, then this capacitance starts to come into the circuit and can have an impact, and we can see from the previous graphs that led to peaking in the response as we started to generate a little bit of instability and resonance due to this being a second order function, and we'll talk about that going forward in a little bit as well. So let me turn the chat on in case anyone's there. Okay, right. Okay, so what we started to do was saying, how can we get rid of some of this peaking? And what we need to do is do some form of compensation. And we noticed that if we started to put very small capacitances in parallel with the feedback resistor, then that affected the response. And we can see that as we change this capacitance from 0.1 picofarads all the way up to 5 picofarads, we change the response here. So and you can see with too much capacitance you start to flatten the response too much, and you're starting to lose the flat bit of the bandwidth that you're interested in. So what we'd like to try and do is try and get this as flat as possible for as long as possible, and try and get an idea of what value of capacitance should be there. Right, so we started to look at this, and we said, well, we're interested in the loop gain. And so let's try and work out what the loop gain of this circuit is. And so we do effectively a small signal analysis on the loop, and we can look at the loop part of the circuit and say, well, if we break the circuit here, so what we've done is cut the wire, and then we look around the loop in this direction, what can we see? And what we see, if we're a signal coming in, is we see the amplifier, which would have a gain of its open loop gain modified by its frequency response, so A0 over 1 plus torr S, and we know that torr is around about 10-15 Hertz for a normal op amp. So that's the open loop response to the op amp, and then we go around, come out of the op amp, and we go through RF, feedback resistor, and then we go down through CS. So what's presented at this point here is going to be, it's a sort of a potential divider, if you like, made up of RF and CS. So the voltage seen here will be whatever the impedance of this is, divided by whatever the total impedance of this loop might be. So we end up with 1 over CS, which is the impedance of CS at some frequency, dictated by S, remember is, J omega in this case probably. And the total impedance, which is whatever this is, which is 1 over CS, S, and this, which is RF. So we've just got this sort of complex potential divider, and that gives us the function around the loop. So if we would connect that back onto itself, that would be the transfer function of this thing. Okay, and then we can rearrange that, and we end up with this A0 1 plus TS to do with op amps, and we end up with this function, which is related to the ratio of CS and RF. And in the case of the compensated loop, when we put our little capacitance in parallel with the feedback resistance, we can do the same kind of analysis. It's a little bit more complicated, but basically we start here, break the loop, come in, and we say we've got the gain of the amplifier again, which in full terms is this expression, and then we've got the potential divider for the voltage at this point will be the impedance of this divided by the total impedance of these two in series. So we've got this and this in parallel in series with this. So missing out all the interim steps, that boils down to 1 over CSS, and then on the denominator, which is the total combination of these two impedances, is that plus that. So that's the parallel combination of these two. And then if we rearrange that with some algebra and manipulation and just get it sorted out and get it into a form which is similar to the one on this side, we end up with this kind of expression. And the main difference to spot here is that you've now got a 0 on the top. We've got some relationship involving S on the top, whereas we didn't have that here. And we've still got a 2-pole function underneath, so this pole's the same on both of them, and then this pole is very similar as long as CS is small with respect to CC. So this is remarkably similar probably to this function depending on the value of CS. Okay, so the difference really is that we've introduced this 0, and the question is, what has that 0 really done for us? And when you can see sort of what it's done, in the case of the uncompensated case with our 2 poles, if we just sketch out some kind of function that's generic for this kind of thing, you can see that we've got flat response up to the first pole. We've got the first pole taking over, which is the op amp response, and then we've got the second pole, which is to do with the input thing coming through, and that drops away there. And the phase response is the interesting one. So the first pole gives us 90 degrees of phase, second pole gives us another 90 degrees of phase, and so you can see we're getting to 180 degrees of phase eventually, and we're quite close to 180 degrees when we're getting to a gain of 0. So that's where the sort of peaking and instability is starting to come into play, because we haven't got very much gain at the point that this is happening. Ah, yes, very true. Okay, thank you. I will get rid of that then. Is that better? Yeah, that's trying to be producer, director and presenter at the same time. Okay, good. Right, so yeah, sorry about that, but I don't think you've missed anything particularly important. You should be able to download the slides actually from either one of the notes pages. But if not, I'll just check that they're there anyway, so you can follow as we're going along. Right, okay, so so we hadn't got to this bit, so that's where I was, so that's all right so far. In fact, okay, what we'll do is we'll just go back, because I was probably covering up this bit of the screen. Okay, so we were just looking at the formulation of this equation and how it looks, and we spotted that this had a single pole response similar to this one, where the coefficient of capacitance, if you like, was both the capacitance added together, where in this case it's just 1. So as It depends if CC is small compared with CS, then this looks remarkably similar to this, just with a 0 in the top, and we were looking at what happens with the 0. Right, so without the 0 we end up with something that is doesn't have much gain or much phase margin when we get to this point here, which means that we can start to probably see a little bit of peaking because the op amp can't really maintain its virtual ground. It's got to try very hard, but it doesn't have very much gain. So that's where the virtual earth is starting to break down. If we then introduce the 0, you can see the effect of the 0 is to actually knock off 20 dBs of slope. So we've got the first one, we've got the second one coming in, that falls down, and then we've got the 0 around about this point, which then compensates for on the poles and reduces the slope. And the phase response is more marked what's going on there. You've got the first one, you've got the second one, and then you've got the 0 coming back in, and it's bringing the phase back up. So suddenly we've got a lot more phase margin, so we should get a lot less peaking going on. Okay, so putting the compensation 0 somewhere near the unity gain frequency is probably a good place to be, and a bit later on I'll put up an example on the web page somewhere that allows you to calculate this in a bit more detail. Okay, so if we look at the closed loop response as the overall system response, you can see then that we're getting quite a nice flat response now before it rolls away, compared with the uncompensated case where, because the virtual earth was starting to fail at this frequency, the capacitance of the source could assert itself and start to introduce a second order response peak in there. So I've managed to get rid of that and smooth everything down quite nicely. So it'd be nice to be able to model the loop gain of the system in a simulator. At least that's what I thought a few years ago when I first started looking at this, because what we just looked at was the closed loop gain, the overall response, the output for a given input. So getting inside the system and trying to see what the loop gain of a simulator of circuit is in the simulator turns out to be actually quite a tricky thing to do, because you need to be able to break the loop to work out what the loop response is. And if you break the loop in the simulator, you physically have to break the wires, and this means that you cannot run the circuit normally because all the bias conditions are not being fixed. So it's not as simple in the simulator as just breaking the wire and looking what's going in. So there has to be a lot of messing about to work out what's going on, but you can do that, and you can see the expression that's being plotted here is actually looks like quite a complicated one. There are simpler ways, and again I will upload, or there is some extra notes on the ECS notes page, particularly about the stability of amplifiers. I think I'll just check it's still there, but it should still be there, which goes into a bit more detail about how to model the loop gain in a simulator, and there's a couple of alternative techniques in there, but this technique was proposed by Mr. Middlebrook going back to 1975 or so you can see that people haven't moved on that much from here. Obviously people don't think it's that important, but if you can model the loop gain directly, you can start to look at the phase margins and the gain margins directly, and you can see here that the phase response of the loop, the black dotted line, hope you can see that, for the compensated case, look, we're getting the 0 compensating, so we're getting our phase back again, whereas in the uncompensated case you can see that the phase is starting to get quite close to 180 degrees or so at the 0 dB point. So the phase margin improvement is actually where we go from this point to this point. The arrow should be lined up, and you can see that we've now got a big phase margin improvement, which will give us a lot more damping. Okay, so that's something to go by and have a look at if you're interested to see how you can actually analyze loop gains. And I'll say there's some notes on the web page that maybe go into a bit more detail on how to actually do that in a maybe slightly simpler way as well. Okay, so that's some points about trying to measure current and effects that may come into play, and with a simple knowledge and understanding you can understand where or how the principle at least that you might want to compensate for it. The detail is in some maths, which is not particularly hard but requires you to just understand what it is you're trying to solve. So the next thing we want to look at is measurement of charge. So charge is related to current because current is a moving charge, and some transducers may generate charge or movements of charge as their fundamental output, and particularly piezoelectric sensors and pyroelectric sensors. So these are ones that detect heat, or piezoelectric detects the amount of bend in something or pressure. So charge is their fundamental output. So we have to think of a way of trying to turn a measurement of charge into a voltage. Sorry, creaking chair. So the obvious way is to maybe store the charge on a capacitor and then measure the capacitor voltage. So that's sort of what we're doing here. We've got a transducer that generates a charge on its plates. When you imagine you squash it and you end up with a charge on its plates. How do we measure that charge? Well, what we do is we would store that charge on this capacitor, so we'd end up with a voltage across this capacitor, and then we can use a voltage amplifier. So this is a standard voltage amplifier to allow that to generate a voltage. And that's what we tried with the current source, and we noticed that that actually introduced a few little issues in terms of this capacitance not being in the virtual ground. We've had to introduce RB here to allow some bias currents in, because as drawn there's no way that we can get DC bias currents into this positive terminal, because the transducer only provides charge, doesn't provide current. Capacitor is, that's just a device in itself, so there's no mechanism for getting bias currents into this device here. So we provide a big resistor to ground, which allows a current to flow through here to allow the bias to happen. Otherwise, if we didn't have this, we would run into problems with this configuration, even though what it looks to be doing is sort of making sense. Right, the problem with putting capacitance here is that we end up with other stray capacitances, because this could be the cable connecting the transducer to the amplifier, so the size of this capacitance may be a bit uncertain for us as well, which is a bit of a problem perhaps. So the solution is to use an op-amp integrator in a similar way to the transimpedance amplifier used previously. So this will look very remarkably similar to the transimpedance amplifier used previously, because we've got a feedback resistor, we've got feedback capacitance, which, remember, in the previous one we were using to compensate out. It wasn't relevant to our measurements. In this case, this is the important part of our measurement, and this is really just to provide biasing. Okay, so we've got a transducer generating charge. We've now got a capacitance which is shorted because of the virtual ground, and what's going to happen is that this transducer will generate a charge, and we will store that charge on this feedback capacitor now. And the op-amp will try and maintain the virtual ground, so 0 volts between these 2 points, so it will adjust its output voltage to maintain the correct voltage across here to maintain that charge. This feedback resistor in this case is really just to allow bias currents into the negative terminal, because otherwise we would have this problem with bias currents. So this is the sort of preferred configuration. The problem being that now, if you look at this, we can see you've got a time constant. You've got an R and a C, and that makes a time constant, and this actually affects the low frequency response of this amplifier, as we'll see. And that can be a bit of a problem, because these charge transducers tend to be used in circuits or systems that are slow moving. They're trying to measure pressures that aren't changing very much, which means that the low frequency response becomes quite important. Anyway, how do we analyze this? Oh, come on. Right. So the basic analysis follows like this. The transducer generates a charge Q. This charge is then stored on the feedback capacitor CF as the op-amp tries to maintain the virtual ground, which is what I said earlier. So knowing that Q equals CV, which is a fundamental equation for charge equals capacitance times voltage, it follows, if you rearrange that V across the capacitor is defined by Q over C. And so V out equals Q in equals minus 1 over C. So 1 over C becomes effectively the gain factor of this amplifier because this is an output voltage related to an input charge. So we get an output voltage related to an input charge, and the scaling factor is minus 1 over C, which is just the value of the capacitance. No frequencies involved here, remember. The resistor is required to allow us to allow the bias currents in. Right. The higher frequency response is affected by the stray capacitance starting to come and play as the non-ideal op-amp frequency effects come into play. So again, we run into problems at high frequencies. This virtual ground will start to break down, and any stray capacitances or cable capacitances will start to come into play, and we might see some interesting effects in the response. To try and get rid of that, it's common to introduce a series source resistor to limit the gain at high frequencies. So that means we'll put a resistor here. And now we've got an RC time constant in this bit, and we'll look at this in a minute. Well, actually what happens is we look at this a bit later in the course, so this is just an introduction to this. And then what happens if you go to extremes, you could see that the gain will actually roll off towards RB over whatever resistance we've put in here, as these capacitances will go high frequency, go short circuit at high frequency. So it will tend towards just being a voltage amplifier then, which means that these effects go away. Anyway, don't worry about that too much at the moment. We will do more on charge amplifiers a little bit later when we do a case study and an example of a real system. So I think the last sort of basic amplifier configuration we need to look at are differential amplifiers. So difference amplifiers are very useful in instrumentation systems. You'll have done this in the second year, I'm sure, but we just need to re-emphasize how useful they actually are. Op-amps have a differential input stage which allow operation down to DC and allow common modes to be rejected, but a standard op-amp configuration doesn't make best use of this arrangement. But you can configure a single op-amp as a true difference amplifier, where it will amplify both difference inputs. Normally one of these is connected to ground in an op-amp, so they're not truly differential. But if you connect an op-amp up like this, then you do get a true difference amplifier, and a difference amplifier means that it will measure the difference between V1 and V2 and give you V out as being an amplification of the difference between these two here. And you can probably see that this is a combination of an inverting and a non-inverting amplifier. And you analyze this, you can do it by superposition, you can do it by nodal analysis. There's various different ways of doing it. I think we probably did it the first year. But in general, V out is equal to collection of resistances multiplied by V2 minus the ratio of these resistances times V1. And if all the R's are the same, if we make R4 equal R2 equal R3 equal R1 and so on, then this will simplify down to V out equals V2 minus V1, which is a difference. So the output is the difference of two inputs. The devil's in the detail, and getting these very well matched to each other becomes the key. If they're not well matched, then they don't perform quite as well as anticipated. There's another interesting case. If you make R3 equal to R4 and just call it RF, and then R1 equals R2 and just call that R, and call it what you like really. If you then do that analysis, and I've done it in terms of G, where G is 1 over R, so it's just to make it easy to write things, conductance rather than resistance, and fiddle that through, you end up with the final answer V out over the difference voltage is equal to minus RF over R. So now we've got a gain factor. Before we only had a gain of 1. If you make all these resistances 1 or the same, you only get a gain of 1. Here we've now got control over the gain of the system by making it RF over R. But remember, RF is the value of two of these resistances, the R3 and R4. So we have to make R3 and R4 the same, and we have to make R1 and R2 the same, and then we get this response out. Okay, so it looks like a simple gain equation for the inverting amplifier, but with a different input. That's one way of looking at it. And the key point here, I suppose, as well, is any common mode signals, which are signals that affect V2 and V1 equally, so a noise signal, if you're picking up noise in the wires and the voltage here is going up and down and this is going up and down at the same rate, that's a common mode signal. They're not amplified because they're not a difference. The difference is maintaining a constant. The difference may be moving up and down in sort of absolute terms, but the relative difference between these two is the same still, and that's the thing that gets amplified. So it rejects common modes. So and interestingly, that includes bias currents. They don't get amplified either, which is good. You don't want that. So if you don't assume an ideal amplifier, you can include A, or some function of A, which is frequency related, and then you get, for completeness, if you want to work it through, V out with some function based on A, or AJ omega, plus V out is equal to this expression all the way through. Now remember, we can simplify this side, but this is the interesting part. If A is not infinite, then this starts to introduce errors. And A, we've already spotted, A is not necessarily infinite at high frequencies. So at high frequencies, this term starts to become significant, and we start to lose the linearity a bit. One of the drawbacks about this type of amplifier is that the input impedances looking into each input are not identical. And this turns out to be a sort of a point of contention if you start looking on the internet for it, because we have to ask ourselves, what do we mean by input impedance? And we're sort of looking into here and saying what resistance we're seeing, but what we're really saying is what's the variation of voltage with current, like here, so dV1 over dI1. So it's the rate of change of voltage with current that we would define as an impedance. So that's a definition that's probably the most useful if we're looking at AC signals with these things. So we can say that the input impedance of this is this is different definition to the previous slide. Let's just go back. So the input impedance looking in here is R1, and this one here is actually a sort of a combination of R2 and R4. And the actual combination depends on whether you define it as a dynamic or a static impedance. If anyone's interested, I found this description on the web, which is the most logical that I've come across. There are lots of arguments about this out there, and this one sort of makes logical sense, really. And this boils down to the R in 1, in this case here, in terms of these definitions anyway, is equal to R1 for AC signals. So it just sees that, and then there's effectively effects of the op amp going on, which really connects it down to ground without anyone knowing. So as far as the signal is concerned, it's seeing all kinds of, it's just seeing R1 as an input impedance, and V2, by the same kind of logic, is really just seeing the series combination of R3 and R4. But you can see if this is varying, it varies this voltage here, which varies this voltage here, and if this varies, this is not varying, then the actual impedance you're seeing through here, if you define it as the difference in voltage over current, will start to vary. Anyway, this is part of the problem of these things, is the input impedance looking into here and looking into here are different. And if you get different impedances there, that leads to slight mismatches in resistances and things, and then you start to lose your common mode performance and run into issues with that. So instead of worrying about what these impedances are and how they affect each other, there's a simple answer, and the simple answer is to buffer the inputs. So we put a buffer on the inputs of both of these, and then we don't care what the input impedances are looking into this amplifier, because the output impedance of this is very close to 0. Likewise here, so whatever these are, they're not going to load it. And the input impedance looking into this is the input impedance of the op amp directly, which is very, very high. And this input impedance looking into here is also the input impedance of an op amp, which is very, very high. And if these op amps are identical, then the input impedances are identical. So that's great. We've buffered the whole thing, and this thing is called an instrumentation amplifier, and this is a sort of a traditional 3 amplifier instrumentation amplifier. So you've got 1, 2, 3 op amps. These need to be connected to power supplies. This is just a sort of a schematic sketch. Okay, all looking good, but we've still got the issue that if we want to change the gain of this, we still need to balance these resistors, and if we want to change the gain, we have to change these in pairs very accurately. So it's a big improvement in terms of input impedances, less of an improvement in terms of trying to make a variable gain amplifier if we want to do such a thing. So it's possible to modify this circuit a little bit by adding just 3 resistors to it. So we've added this resistance, and this resistance, and this allows us to change the gain of the amplifier by only adjusting one resistor, in this case RG. So if we made RG variable, we can now change the overall gain of this amplifier. So a bit of explanation. The virtual earth at the input ensures that point A must be at V1. So this is a virtual earth here, so whatever the voltage is here must be the same as the voltage here if the op-amp is operating in this linear range, which means that point A is at input voltage V1. Likewise, point B is at input voltage V2. Therefore, the voltage drop across RG is the input differential voltage, so this is V1 minus V2 across here. Okay, this voltage difference causes a current to flow through RG, and this current must also flow through both RDs, and that allows us to then get some input into the difference amplifier. And then if you want to do the maths to show what's going on at that point, you can say that I through here is going to be V1 minus V2 over RG, and then you can work out voltage between points 3 and 4 on here. Put 3 and 4 on here because it's IRD and IRD plus R voltage across RG, which happens to be V1 minus V2 as we've just established. Then you can run that through some basic manipulation and you end up with the voltage going into the op-amp is then V1 minus V2 1 plus 2 RD over RG. Thus, the voltage presented to the following differential amplifier, which is this bit here, is an amplified version of the differential input voltage. Yeah, differential voltage multiplied by some factor to do with the gains. Okay, so we can just we can either alter RD or RG to change this overall gain factor. Makes more sense to change RG because there's only one of it than to change RD because there are 2 of those. We have to get them matched, and then we can just fix these other ones at whatever value we like. So we have a fixed gain stage here, and we vary the size of the signal being presented to it. So we've already seen the gain in the following stages minus RF over R. So the total gain as drawn will be V2 V1, the gain factor introduced by this new front end, and then we multiply that by RF over R, and there's a minus sign missing in here, just noticed. But the principle still holds. So this is a nice way then of making quite a good high impedance amplifier with variable gain that's only adjusted by one resistor, and so you can spend a lot of money on your manufacturing process to make these resistors all the same. And in fact, if you buy an instrumentation amplifier in a package, so it looks like an op-amp package, a little black package with 8 legs, you will find that there are 2 terminals for you to connect your own RG to it, and all the other resistors are inside the package and have been laser trimmed at the factory to get very good response. So all you've got to do is apply RG and twiddle that around. You can build it yourself, but you'll get better performance from an integrated one. So use of the differential amplifier will be usually in a bridge. A bridge, we can have a full bridge or a half bridge, and I'm sure you've done bridges before. A full bridge with fully differential inputs is the best solution, gives you better sensitivity. And load cells are a typical thing that will generate a differential signal. There's a picture of it somewhere. Right. So this is the type of arrangement. This is a bridge. And so you arrange for these 4 resistances to alter, and if one goes up and one goes down, as it's shown here, and the other way around, this one goes up and this one goes down, you end up with an increase of sensitivity, and you measure the output or the imbalance of the bridge between these 2 points here. And a half bridge is just one where 2 resistances in the arms are the same value and never change, so you fix this at a point halfway between VCC and ground, and then the sensor has its resistances which change up and down accordingly, so this voltage will just go up and down accordingly, and you'll measure the difference with respect to this point here. So for a half bridge arrangement, you can do a very simple analysis. showing what's going on. So you just calculate the various voltages between V1 and V2, and then you want to calculate the difference between V1 and V2, and that boils down to these changes. So delta R will be the change in the resistance to the sensor when you apply, say, pressure to a load cell. And if you run that through, you end up with a sensitivity that's saying the change of resistance divided by 2 times R, where R is the resistance of the overall system. And it's very, very straightforward, and it works quite nicely, and it's quite a good way of getting a differential signal based halfway between the supply rails. And if you do analysis for the full bridge, very similar, it's just doubling up on everything, but what you get is a fully differential signal. So now you've got a sensitivity which is twice as much as the half bridge, which is great for sensors that don't change their resistance very much. You double your sensitivity at the front end, reduces the noise, which is great, and then you can amplify that through your differential amplifier. Again, you reduce the noise even further then, because the signal you're trying to measure is a differential signal, and any noise is a common mode signal. So anything that's got good common mode rejection and amplifies differential signals is absolutely great in those situations. So you can see how all this is sort of coming together now, with an understanding of what a common mode is and a differential signal, and you can end up with a system that's very good at suppressing noise and amplifying a very small signal. And it can be that the signal is so small that you can't see it in the noise by eye on an oscilloscope, but such a measuring system, we're very good at extracting that signal because we know the signal is differential and we know the noise is common mode. Right. So as another point, the half bridge, and I sort of alluded to this, is very useful in situations where the sensor output can go up or down, as it effectively biases the sensor output midway between the supply rails, and then we use a differential amplifier for that. Part of this comes from the fact that these days we like to operate op amps on a single supply. I can't remember if this is this course or previous course where we talked about supply rail issues. Might be a different course, but if you operate an op amp on a 0 to 5 volt supply or a 0 to 3 volt supply, if you want to operate off a battery, then it's tricky because most inputs tend to be referenced to 0, and if that's the case, then you need an amplifier that can measure down to 0 volts, which is your negative supply rail, accurately. And not all op amps can do that, so you have to end up buying single supply op amps and making sure that it is actually truly a single supply op amp. This technique of using a half bridge allows you to effectively bias your sensor halfway between the supply voltages, and any changes in the output then are referenced to halfway across the supply, which means that you can use any op amp at that point to see a signal output. Okay, so it sort of swings and roundabouts, but it's important to know your enemy, and that's an example. Yes, it is true. We do an example on that a bit later in the course, where the importance of this comes out. So that's useful. Right. So on to a case study to see how some of these techniques can be brought to bear. An environmental monitoring system. So there's been a little bit of introduction to this because this is some of my research. Sensors for environmental monitoring, all useful, particularly with the climate change going on. We'd like to know what's going on in the environment, see what's going on. So as an example of a signal conditioning system, we're going to look at a system using a chemical sensor for environmental monitoring. So don't worry if you don't know anything about chemicals. That's really not what we're going to worry about. The sensor needs to be cheap, robust and long-lasting, and needs to be compatible with wireless sensor networks. You know, we're not particularly worried about that in this course, but that's the overall problem we were trying to deal with. And what we'd like to do is stick these sensors in the ground in fields all over the place, and then this allowed us to generate a real-time map of the environment, so we know what's going on. Because believe it or not, people don't really know what's going on out in the environment. It's at such a scale. Satellites will view the ground from a great height, but they'll only show you 20 meter squares on a good day, and if there are clouds in the way, that stops it if it's a visual sensor. So there's still a lot of scope for sticking sensors in the ground to see what's going on. And in this case, what we're interested in is how much salt there is in the ground. So we want a sensor that's sensitive to salt or chloride in this case. So that's where we're going with this. So to be able to use this sensor and define a signal conditioning system, we need to understand the sensor and what it is we're trying to measure. And in this case, this sensor is a potentiometric sensor, and that means it generates a voltage in response to whatever's going in. So you get more voltage out of it if there's lots of chloride in the soil or the ground, and you get less voltage out of it if there's no chloride in the soil. And it's sensitive to chloride, and it's self-generating, which is an interesting one, as the voltage it generates is due to a chemical reaction on the surface of the sensor. So it's inherently low power because it's actually generating its own power. It's using the salt in the soil to generate a voltage. So it's a bit like a sort of a battery in some respects. So we're getting an idea that this thing is a self-generating sensor, and we have to understand a little bit about how that actually works. So I'm not going to go into the details of this, but there's a reduction oxidation reaction between silver and its salt, silver chloride. And so what we're actually measuring is this potential of this reaction, and you can see here that there's a reaction rate depending on silver chloride and the concentration of silver and the concentration of chloride. And so if you change the concentration of chloride, which is the thing we're interested in, it changes the ratio of this log function, which eventually changes the voltage that's being generated on the sensor, and these are all hopefully constants. So maybe you didn't think GCSE chemistry was going to be of any use to you, but actually it turns out that there's a lot of chemistry in electronics anyway, because fundamentally chemistry is just a movement of electrons. These are just ions down here. Right, so if you do the sums on that, it simplifies down to the voltage you get out, E, is equal to some constant depending on what reaction you're dealing with, and then this thing which is 59 millivolts of change for every decade change in the concentration of chloride. Okay, so the chloride concentration is changing, the voltage that you're getting is changing, and we just need to measure that. So varies by 59 millivolts per decade change in chloride ion in ideal conditions. Right, so we know that this thing is going to generate it. Let's just quickly look at how we might make this. You might find this interesting. We want a robust one that's cheap, so we ended up printing it. So we ended up with an aluminous substrate, so that's a bit like a tile, like a ceramic tile, small one in this case, because we're only about we're a few millimeters, 5 millimeters across here, 2 or 3 centimeters long, probably 3 centimeters. And so we take that and then we print down an insulation layer. We print down first a silver layer, because this is a silver chloride system. So we print down silver, which is a nice conductor on here, and then we print down some insulation, and then we print a layer of silver and silver chloride mixed in here through this hole. And when it looks like this, you end up with this flat surface with a small sensing hole down here, and any chloride from the environment that then sits on this surface will initiate that reaction, and a voltage will be generated at this terminal, which we can then try and measure it. Trouble is, we don't know what we're measuring this potential against. It says here, consider the sound of one hand clapping and you'll get the idea. What we've done is we've made half a battery, and these sensors as constructed only have one wire. So how do you measure against that? What you're measuring it with respect to? So we need to create another one. So what we do is we create a reference electrode that generates a known potential. We have our chloride one that varies with the chloride, and we end up with this sort of electrical circuit in the soil, and we can measure the voltage between these two terminals, and that's what we're interested in. Right. And so basically we do exactly the same thing. We create an electrode that's sensitive to chloride, and then we make sure that we've got a known concentration of chloride around it, and that just generates a potential for us to measure against. So straight away we're getting a differential signal that we're interested in. We've got a potential based on a fixed concentration of chloride that we've managed to mix in with this area here, and we've got a varying voltage depending on the chloride in the soil. So that allows us to measure the change in the chloride in the soil, and we can print these things side by side. In this case, this is our reference one where we've created some porous glass. We're very proud of this porous glass. Making porous glass is actually quite a tricky thing to do. So it's like a sort of a glass sponge. So then we can soak it with our known chloride solution. We can then put a polymer cap on the top to stop it leaking out, and that makes us our nice reference electrode. And then the silver chloride one is the same as we've seen earlier. And we end up with a nice little sensor with the differential measurements made between these points here. It's all on ceramic tile, and it's made of glass, which is quite tough, so the whole thing is quite tough and robust, and it's actually very cheap to make. So tricky, and that's part of it. That's just making the sensor. Sensors are always difficult to make. So we just need to measure this fixed potential now. So in order to do this, a differential amplifier would probably be a good idea. But we don't know how much gain is needed. We don't know how much signal comes out of this. We've got some idea. We know it's 59 millivolts per decade change. So we did some tests, and here are decade changes in concentration of chloride, milligrams per litre. So tap water is around about 8 milligrams per litre. So this is tap water, and then we start to get salty soils, and up to a point probably about here or so where crops stop growing because it's too salty. So we're going to be operating in this kind of range, and so we know that we're going to be getting out potentials from our testing of around about 100 millivolts up to about 250 millivolts or so. So that's the sort of range of voltages that's coming from our sensors. So now we can actually calculate the gain needed in our differential amplifier to get it up to say 3 volts for a system for us to look at. Okay, so as I just said, from this we would expect a range of about 0 to 300 millivolts or so. That would be a good range to have as an input signal to our op-amp or our amplifier system. We probably want to put that into an analog to digital converter operating at about 3.3 volts. So we want a gain of about 10, because that gets our 300 millivolts up to about 3 volts, and that allows us to use the full range of our converter. So we start to define that we need a gain of 10. Noise might be a problem, so perhaps we will want a differential system, and maybe high input impedance is what we want as well. And as we're looking for very slow moving signals, so chloride in the ground doesn't alter very much, the filtering can be crude, and we'll look at that as we go forward a bit. Right, so in practice, if we take a reading every hour, but each of those readings is made up of the average of 10 ADC conversions, we improve the signal to noise ratio. And I think what I'm going to do is stop at that point, because people lose their interest towards the end of a lecture, and this is an interesting point to get over. So at the next lecture we'll just pick this up, and this will allow us then to understand how we're improving our signal to noise, and by then you might be interested in it rather than bored. And then we can see how we constructed the rest of the system and how well it actually performed, what mistakes were made and why we made them, and that's quite an important thing to go forward as well. So I think at that point we will stop, and we'll pick that up next week, and I hope you found that interesting.